is that I'm going to look at the turquoise region. And the NP ratios. I gotta bring that. So let's think about this. So what do we know? We've already said it, but I think we should say it again. These are neutron rich, unstable nuclei that go beta decay. So that means here is that when you do this, they go beta decay because why? They go beta decay because it's the fastest, the quickest way to stability. And that means that you have to do what? You have to lose a neutron and gain a proton. But what that means here is that it really means this here. So in terms of the NP ratio, look what it says here. Now remember, it's the number of protons and number of neutrons that we're looking at. So remember, NP is then going to be the number of neutrons divided by the number of protons. But in the turquoise region, what we're finding here is that what? This guy right here, this is too large. This guy is too small. So what beta decay does is it has to reduce that number. So then when you do a beta decay, how does that change that number? Well, it reduces the ratio NP. So let's go look at this as an example here. And the first example that we want to look at is we want to look at carbon. We've already done carbon. And this is one of the most important isotopes for investigating the past of human development. So here we go. Here's an example. And the example is that we want to look at carbon. So carbon really has three isotopes. There's one that you can make, but there's three natural isotopes of carbon. So what we want to, what I'm saying here is that there are three isotopes of carbon. It's carbon 12, 13, and 14. So let's go look at that. So if I look at this, I'm going to paste in my carbon symbol right here. And so these guys are carbon 12, carbon 13, carbon 14. Now let's go look at these guys in detail. So if I look at these in detail, then I have the following thing. I see that carbon is 6. So then that means 13 has to be 6, and then 14 has to be 6. Let's look at their NP values here. So if I look at their NP values, I then have what? I see that this guy has 6 neutrons, 7 neutrons, 8 neutrons. And because it's all carbon, they all have to have 6 protons. So if I look at these details now, we want to calculate the NP values. Okay. So if I look at that, let's look at the first one. This is NP. This is going to be 6 over 6. So that's exactly 1. This is NP, and this guy's going to be 7 over 6. And this is going to be 1.17. And then if I calculate this guy, you can see that this is 8 over 6, and this guy's 1.33. Now, let's go look at that. This carbon is less than 20. What did we say about less than 20? If it's less than 20, they're most stable when the NP value is about 1. Right? So, since this nuclei is less than atomic number 20, this implies that the most stable is NP approximately equal to 1. So what you're seeing here is that carbon 12 and 13 are close to NP equal to 1. Whereas carbon 14 is far away at NP equals to 1.33. So what I would expect here is that these guys should be stable because their NP value is like this. This guy tells me that it must be unstable. So then I go into Wikipedia, and here's the isotopes. Here's the main isotopes of carbon. And you could see, you know what, I created this earlier, and I have this yellow that I'm going to bring over, which I did not it did not come over when I copied the image. So let me go put this guy in here. And so what you're seeing here is that, look at what's stable, right? So from Wikipedia, what this is telling me here is that just by looking at the NP values, yes, 12 and 13 are stable. And the reason why they're stable is that their NP values is close to 1. But here we see that carbon 14 is radioactive and undergoes beta decay. And so what this is really telling us here is that the NP value is too large. So that means it has too many neutrons and too few protons. So beta decay actually does that nicely. And we can see here that it decays to nitrogen, as we already discussed. So when I look at carbon and it does this beta decay, what you're seeing here is that it goes to nitrogen. So when I look at these numbers and I start to compare them, we could see here is that we have 8 neutrons. This guy has 7 neutrons. This guy has 6 protons. This guy has 7 protons. So it's moving in the direction that it needs to be at here. So when we're looking at this thing, then of course this emits the beta plus the energy here. But what we want to look at is we want to look at the MP value, right? Look at the MP value. So it goes from where? NP equal to 1.33, and now it goes to NP equals to 1 exactly. So you're seeing exactly what you're supposed to be seeing in beta decay. It's moving to that line of stability here. So what I did here is that I went in and I looked at this guy. And if you look at this thing, what am I seeing here? I'm seeing a couple of things. One, look at where carbon-14 is at. Carbon-14 is exactly where? It's right here. This guy is carbon-14. And then what's it going to do? It's going to decay to right here. It's going to be right on that black line. And so this black line tells us here that this guy is 14,7 nitrogen. So what you're seeing here is that you're seeing this jump now. Look at the jump. So the jump is going like this. It's jumping from here to there. Uh-oh, that's not very big. I don't know what's going on. So it's jumping from here to there. That's that jump to the black line of stability.